We're going to start with a review of expected value. To skip this and go straight to the problem solution, look for the link in the video description. Let's say you have a fair die and X is the result that you get when you roll the die. And let's say you have a fair coin and Y is going to be 0 if you flip a head and 1 if you get a tail. And you are interested in knowing the expected value of the sum of these two outcomes. We define the expected value as the sum of the probability of each of the possible sums multiplied by the value of that sum. If we list all of these outcomes out, we get that the probability of rolling a 1 is 1/6, and the probability of flipping a head is 1/2, and the sum of those outcomes is 1 from the die and 0 from the coin. We get the same probability for rolling a 2 and flipping a head, and so on for rolling a 6 and getting a head. To that, we add all the outcomes that we get when we flip a tail. These probabilities are the same. We can roll a 1 and then flip a tail, roll a 2 and then flip a tail, and so on. Let's factor out 1/6 times 1/2, which appears in all of our terms. And the sum of our outcomes when we roll a head is the sum from 1 to 6. And then when we roll a tail, it's the sum from 2 to 7. When we simplify, our expected value is 4. Now let's take these expected values separately. First, we'll evaluate the expected value of rolling a fair die. Since each of the outcomes is equally likely, I'll go ahead and factor out the 1/6 probability, and that's true for all 6 possible values. This is 3.5. Let's find the expected value of y, probability 1/2 for either a head or a tail. Notice that the sum of these two expected values is equal to the expected value of the sum we found earlier. We can generalize this, but I think it's pretty clear because expected value is a linear transformation that this is going to be true. Let's go to the problem. Since we're counting consecutive pairs, let's call P1 the first consecutive pair, 1 and 2. P2 is going to be the second consecutive pair, 2 and 3, and so on. We have 29 consecutive pairs, ending with 29 and 30. Let's let S be our set of 5 distinct integers chosen from 1 through 30. And let's say that if one of these P sub i's is a subset of S, then we're going to define xi to be equal to 1 in that situation. Otherwise, that xi is going to be equal to 0. So for example, if the numbers 1, 2, and 3 are a subset of S, then we have x1 is equal to 1 and x2 is equal to 1. And if our other two numbers in the set are not consecutive integers, then all the other xi's are going to be equal to 0. So we can take x1, x2, all the way through x29, and that is going to give us the sum of consecutive integers in our set. The problem asks for the average number of pairs in our set of 5. The average is the same as the expected value, and when we sum over all of these xi's, depending on which one of these turns up to be 1 and the rest turn up to be 0, that's going to be the number of pairs in a given set. Since the expected value of a sum is equal to the sum of the expected values, we can now find the expected value of each of these individually. Let's start with the expected value of x1. This is the probability that our first consecutive pair, P1, is in our set of 5. And we multiply that by 1 because that's the value that x1 takes when this occurs. So the probability that 1 and 2 are contained in our set of 5, it's going to look something like this. 2 of our elements are going to be 1 and 2, and our other 3 elements are going to be any other 3 numbers out of 30. With 28 numbers left, we have 28 choose 3. So this probability is 28 choose 3 out of all the possible subsets chosen from 30. Let's go ahead and simplify this. 28 choose 3 and the reciprocal of 30 choose 5. Let's cancel out these terms. In the numerator, we have 20. In the denominator, we have 30 times 29. We'll simplify. Let's find the expected value for x2, which is the probability that 2 and 3 are in our subset, multiplied by 1, because that's the value that x2 takes on when this is true. We have 2 of our numbers are 2 and 3, and we can choose 3 out of the 28. So it turns out that this probability is the same as it was for x1. In fact, this is true for all 29 of the xi's. The average number of pairs is going to depend on which of these 29 xi's is equal to 1. All of these expected values are the same, and we have 29 of them. The 29's cancel, and we're left with 2/3, which is option A.